So we are happy to have Sasha Goncharov from Yale. The title is on the screen, but actually it's different from the title which he gave early. But anyway.
Yes, and the title which I gave early more kind of relevant, but this is shorter.
Okay, yeah, this is shorter. Okay, Sasha, please.
Okay, so I'm going to talk about joint work with Maxim Kontsevich, and this was ongoing project for about a decade, and so there were several goals. So one of them was to develop geometrically this non-commutative cluster varieties, but I want to start from a different perspective and to explain somehow one of the points which you can see this way. So let's suppose that you have a holomorphic vector bundle over a Riemann surface. So this sigma is a Riemann surface. And this is a holomorphic rank M vector bundle with any singularities.
Singularities addressed to the connection. Yeah,
Yes. Vector bundle with connection. Actually, thanks. I didn't say this. With connection, with meromorphic connection, with arbitrary singularities. So on this Riemann surface. So if you have, so this is the most general linear differential equation of rank M. So if you have such a data, then it is well known, goes back into the 19th century, that you can assign to this some space, a point in some space. So the space of Stokes data. I'm not going to define what is Stokes data, but in particular, it contains inside the monodromy data. So I just call Stokes data the whole thing. And the monodromy data, this is just a local system underlying this holomorphic vector bundle with holomorphic connection. So this, again, as I said, I'm not going to define, but I want to make a statement about this. So this Stokes data, it depends on two kinds of parameters. It depends on a discrete set of parameters and also continuous parameters. And what are the discrete parameters? So you have, first of all, the underlying topological surface, which usually will be denoted by S. It comes with the punctures where you have connection have singularity. And if we would have regular singular differential equations, this would be it. If we have Stokes data, then there is some kind of data which you can account by some kind of braids sitting around this point, just this kind of curves, which always go to the right and have some property like they're connected. So we can call this data L. So this is the isotopic class of this data is a discrete set of parameters. And on the other hand, it has continuous parameters. So
sorry to interrupt you. I'm confused. This set of curves, it's not really continuous and unless you fix, not really discrete unless you fixed, or you just consider, it depends on the irregular type.
Yes, I'm sorry, I'm from home, so I need to.
Okay.
Make a token phone ring. So I said it depends on homotopy class of this red curves. This is discrete data. Jan.
Yes, but I think that even the homotopy class, I mean, it's continuous. So your irregular data, it's sort of a negative piezo polynomial. It's
Exactly. But this negative piezo polynomial, it depends on discrete data and continuous data.
You separate, okay.
I separate them, that's the point.
Okay. Mm-hmm.
The discrete data is given by some homotopy classes of some curves in tangent space, or you can say in tangent bundle of tangent space. But the continuous data is huge manifold. This is the moduli space of Stokes data, and this discrete data just parameterize different components of the space. And so this big space is fibered over another space, which I call, let's say, mod L something. L is just this notation for the component where you see it. And this moduli space is a certain fibration of the usual moduli space MGN. And so altogether, given discrete data, we observe the following, that there is this moduli space, which I just introduced on the right. Moduli, I didn't introduce, just said that it exists, which is fibered over MGN. And then over this moduli space, there are two things happening. So first of all, there is so-called the RAM local systems. This is all local systems I consider, but I just sitting on a given component. All possible holomorphic vector bundles with arbitrary connections. But if I take some component, I get this component of the space. And on the other hand, there is this Mbeti, again, component of this Mbeti. And then the key fact is the Riemann-Hilbert correspondence, which says that they're analytically the same. And the key point that this right-hand side, it's a local system of moduli spaces. So this guy is what I call its fiber is a moduli space of Stokes data. It's stack of Stokes data of given topological type. And so I wanted to make a statement about this guy. So, but before I make the statement, there are some notations. So if you take the fundamental group of the underlying MGN, this is a standard mapping class group. And if you take the fundamental group of the biggest space, which I didn't quite define, but refer to it, that's important for me object. This is a wild mapping class group. And so saying that this is a local system is the same thing as to say that you have one moduli space of Stokes data of some particular topological type, and the wild mapping class group acts by certain transformations of this moduli space. That's the same thing. And now the statement, before I formulate the statement, I want to talk a little bit more on some other preliminaries. So let's suppose that you have a skew field.
Can you recall to the graduate students what skew field is?
Yes, skew field is a non-commutative field, although it sounds weird. So for example, quaternions. Could be C or quaternions. Or you actually, I don't insist this is a field, so you can take matrices and by matrices over some field. But then whenever you work with this, you assume that you can invert some matrices which appear in your story. There will be finitely many situations where you need to invert them. And so you can do it like that. So when I say non-commutative variety, so what do I mean by this? So I can take its R points. And so here's, and for example, you can take C points. So this is the usual variety. Then you get usual variety.
So your R is different from R, which is one line above?
It's the same, just my handwritings.
Okay.
usual variety over complex numbers if you take complex points. And here is an important for us example. So let's take a moduli space of one-dimensional vector bundles with flat connections over this R, for example, over quaternions on a unit circle. Then if you want to, so this is a typical non-commutative space. And if you want to take its R points, then it's not R star, as you might think, it's R star divided by R star conjugation. It's a very important remark for us. So X R X inverse is equivalent to R when R lives in this R star. So that's an example, or you can elaborate this example a little further. You can take gamma to be a graph, any graph, and we can introduce notation flat families of flat vector bundles with one-dimensional fibers. And
when R is the matrix range, so the R star, you want to take all the invertible matrices.
Sorry, once again, because I didn't hear you.
If R is the matrix range,
yes,
then you will take R star to be the all invertible matrices on the conjugation. Right?
Then I take to be invertible matrices.
Okay, got you.
Mm-hmm. And if this is a graph, so you can do the same thing. And then you get this non-commutative variety of one-dimensional R local systems. That's moduli spaces of flat line bundles on gamma. When I say line bundles, I mean line bundles over our base ring R, if we take R points. Okay, now why I introduce this moduli space of Stokes data? Because there is a general statement about this, which is one of the consequences of this story, that there is a canonical non-commutative moduli space which one can call this M Betty, and I put here non-commutative to emphasize non-commutative, and it depends on whatever discrete data you have. So in this case, discrete data, I should elaborate a little more. So it depends, of course, on your surface S. It depends, of course, on the rank of your bundle, and it depends on this curves, which are commutative class of curves I was referring to. So this is a moduli space of framed, I'll explain what framed means a little later, Stokes data. And moreover, it carries a natural non-commutative cluster Poisson structure. So I have to explain what is cluster Poisson structure. That's one of the goals, but you'll see this later. And now, most important statement here, I mean, two important statements, that it has cluster Poisson structure, and the second is that it's equivariant under the wild mapping class group. So this statement is actually new, even the case if you consider R to be complex numbers. Then it just says that moduli space of usual Stokes data always has a cluster Poisson structure. And in special cases, this is well known. So if you consider the regular case, this was our work with Volodya Fogg. If you consider, I guess, generic Stokes data, then there was a work by Bolch, which says it's Poisson. But in fact, this is true that it's not just Poisson's cluster Poisson, And one of the consequences of this, it can be quantized always. Quantized in the sense which we talking about when they do cluster quantization with Volodya-Fock. So it can be quantized always. And the quantization is equivariant under this wild mapping class group. And there is also there is a flavor of this theorem. There is some Moduli space, it has natural cluster A variety structure and so on so far. So why I mention this, because if you go to A flavor, that when the rank is 2, we get structure which is essentially Berenstein-Retach non-commutative cluster algebras. Cluster algebras, they call it, I guess, surface cluster algebras related to surfaces. And also in general, in the all this in the A case, is have canonical coordinates which are described via quasi-determinants. There's this Gelfand-Retach quasi-determinants. And so they appear very natural in the story, and moreover, they appear together with their properties, so you don't have to worry about formulas. Geometry suggests you what's going on.
Sasha, what is R in this case? For
R is arbitrary non-commutative field. Yeah.
For Berenstein and Retach.
Yes. That was their goal. Arbitrary non-commutative skew field.
Okay.
Hmm?
Yeah. Okay.
Yeah. Actually, this whole project, so it started somewhere like 2011. So, and the goal was to get this quasi-determinants and this kind of surface cluster algebras to explain that they're just geometrical realization, that they have geometrical realization which provides all the formulas and provides a geometric treatment. But it goes beyond this, beyond M02 case. It actually always true. So as I said, this is true for any. So now, once again, so for any Moduli space of Stokes data, it has this cluster Poisson structure, and therefore can be quantized, and it has upgrade to non-commutative space, to certain non-commutative space.
Excuse me, does it have any consequences for the DRAM part? These texts, they are analytically and isomorphic, so then on the DRAM side you also have some kind of additional, or it cannot be formulated intrinsically. It's only kind of bundles with regular connections such that their Stokes data belong to the cluster chart. It's only in this way.
I mean, the statement, if you go to, if I want to be correct and more specific, okay, well, all right. So if I'm talking about a commutative case, and you probably refer to commutative case because nobody usually consider non-commutative DRAM data.
Yes, commutative.
Sorry. Then there are coordinates on the right-hand side. In the commutative case, there are cluster Poisson coordinates and there are cluster A coordinates, both kind of coordinates. They exist. And cluster Poisson coordinates, they're really on this Moduli space of frame Stokes data. And so you can pull them back and get certain analytic functions, no longer algebraic, of course, because Riemann-Hilbert is transcendental correspondence on this space. So that's one of the consequences you have, if this is what you're asking. And you can go further. For example, everything where cluster coordinates appear in the usual situation. For example, you can go to this Gayoto-Mornetsky setup, and they use cluster coordinates this or that way. So it all should be extendable to this DRAM data, and I believe this maybe it's known to some extent. But all I'm just saying is that this, I just want to make this point once again. So first of all, this Moduli space has Poisson structure, and most importantly, it has cluster Poisson structure. And so this shows that cluster Poisson structure is not some kind of artificial class of Poisson structures, but actually in this setting, all of them are cluster Poisson. So that's the point. And as I'll try to explain a little later, they're not just cluster Poisson, they're cluster Poisson in a very specific way. So they all come from this bipartite ribbon graphs. And this also buys you another thing. So you can talk about these three-dimensional Calabi-Yau categories, which automatically appear just from the fact that they're described by Riemann graphs and so on and so far. But I don't want to go too far in this direction. So I explained what the, so to speak, one of the consequences. But on the other hand, I want to make the talk very, very elementary. And so now I start the part of the main talk. And so I want to discuss a key example which explains to you what happens. Are there any questions so far? So this example is a spectral description of generic triples of flags in non-commutative setting. Whatever I'm going to say, it's a non-commutative setting. And so it looks as a very special example, but as you will see, this is actually the main building block of what's going on. So let's start. So let's suppose you have n-dimensional vector space over R. And we talk about flags. So a flag.
Vector space over R means free R module.
Yes. Thank you. Free R modules. And then what is a flag? So it's the usual definition. It's just a filtration by R submodules, which I need to introduce to make sure you see the notation, which I use. And so here the codimension, the filtration is decreasing, and the codimension of Fi is I. And I also often use notation where I of such a flag given by Fi divided by the next one, Fi plus 1. Okay, now I won't talk about triples of flags, but is there any simple example? If you talk about just flags, that's not interesting. They're all the same, obviously. If you're talking about pairs of flags, that's a little more interesting. So let's look at this. Generic pairs of flags. So let's denote them AB. And what does mean generic? Generic is the following definition, that if you have your vector space, you can project to quotient by subspace of one flag and to the quotient by the subspace of the other flag. You can take map to the direct sum of these quotients, and the condition is that this must be an isomorphism for any integers a and b such that a plus b equal to m, non-negative integers. That's generic. Now, how we describe them? So here is a lemma. So if you consider groupoid of generic pairs of flags, let's call them AB. This is the same thing, meaning there's canonical equivalence as groupoid of ordered collections of lines, R lines. For the last time, I emphasize this R. And so this is L1 and so on Lm. That's the lines. So how this correspondence works? Very simple. So you take intersection of A sub A with B sub B. So before it was written for the case when A plus B equals to M. Now I want to do this for the case when A plus B equals M minus 1. And A and B as non-negative numbers. Then if I consider this intersection and call, I wanted to denote it by LB plus 1. So it sits in my vector space. And these are the lines. So this means that these are the lines L, which you see on the right-hand side. Now, yes?
Excuse me, can I ask a question? Is A index A of rank A or co-rank A?
So this is codimension.
Co-dimension. Okay, thank you.
Thank you for the question, because that's a very good point. So codimension. You see it because the indices of the filtration are upstairs. This means it's decreasing. Then this vector space you can reconstruct as just sum of these lines. If you have all of them, that's the inverse functor. And the filtration are the filtration which goes one way from the left or the other way from the right. And so this functor back and the functor forward is just given by this formula. Okay, so that's equivalence. So this is very easy, so no parameters. Now, how about triples of flex? Well, so we denote them A, B, and C. And we want to introduce the notion of generic. So when we say generic triple of flex, we mean the following, that for any three numbers A, B, and C, such that their sum as before is M, and this A, B, and C are non-negative, we have the induced maps now to three spaces, to V divided by codimension A guy of the first flag, plus V divided by the codimension B guy of the second flag, and V divided by the codimension C subspace of the third flag, and this must be an isomorphism. So that's a condition. And this means generic. Generic means that this natural map is an isomorphism. Actually, there is a subtlety here, because when you talk about flex, you can dualize, go to the dual vector space and take the induced dual collection of flex given by orthogonals, so to speak. And then generic in this sense is not going to be in general generic in the sense of the dual space. So there are two natural notions of generic, not one. So it's not a self-dual notion. Okay, now I want to describe them. And for this, I want to draw a certain picture. I want to draw a certain graph. So I take a triangle. And I want to describe what happens in the case m equals to 2. And then I wrote the following black and white graph. It's called bipartite graph. So you have this kind of vertices, black and white. And if you wanted to see the pattern, then let's do it in the m equals 3 case. Although probably you already guessed what the pattern is. So in the m equals 3 case, we have 3 black points on the sides everywhere. And then we connect them into bipartite graphs. So just like we were doing before. Okay, and now we make a bipartite graph, so it's going like that. Okay, and so on. And now comes a theorem. This is first main theorem. So theorem A, that there exists canonical equivalence between the following groupoids. So one of them is groupoid of generic triples of flags in some vector space of dimension m. I don't have to say, I would rather say, I don't have to specify the space in an n-dimensional space, vector space over R. And on the other hand, so that's where the interesting things appear for the first time. So you have to consider flat line bundles over or on the graph gamma m. Of course, there are line bundles, so R is everywhere. Now let's see. So what do we get, for example, when m equals? So when m equals 2, we got nothing interesting because this graph which you see here is contractible, so there are no line bundles, and so but then the result is still non-empty. It says that all generic triples of flags are equivalent. I also want to stress that this is a one-to-one correspondence, that given this notion of generic, this is a one-to-one correspondence with local systems on this graph. But when m equals to 3, there is something happening already, because in this case, the right-hand side is a local systems on a circle, which we discussed before. And so, as I said before, this is just R star divided by R star conjugation. And if R is commutative, therefore, in general, we have actual coordinates. We have m minus 1, 2 is the number of holes, coordinates, canonical coordinates. So they are just monodromies around the holes. But if, and these coordinates in this commutative case, this is the ones defined by Lodefok and myself long ago. And they're precisely these coordinates. But when R is non-commutative, there are no coordinates because you're talking only about numbers in R star modular conjugation. So there is no natural way. How can you extract numbers from this? And so no coordinates. So this is the first kind of major upshot. There is no coordinates, and so the whole language of cluster story has to be rewritten in the terms of this line bundles, but you cannot talk about coordinates at all. Okay, so now let me prove this theorem. So the theorem is non-trivial, but the proof is easy. So it's so easy that I can present it completely. And so let me do it. So first of all, I want to define one of these functors, so I call it functor L, which goes from generic triples of flags to a flat line bundles on the graph gamma m. Well, so first of all, let me recall what is a flat line bundle. So we're talking here about flat line bundle on some graph. And so I recall that a flat line bundle on a graph is the following data. That first of all, for any vertex V of gamma, you have to assign a certain line. That's called LB. It's a line. And then for any edge, let's call it E of gamma, you have to assign the parallel transport. So you have this edge with coordinates V and W, that's my HE, and you have to assign transport from LV to LW, this certain isomorphism. And so that's it. So you just need to produce such a data. And so, okay, how to construct such a data if I have my bipartite graph? So again, the drawback of doing this talk, on Zoom is that you see only one screen, but the good part is that I can copy. So let me do it. Okay. So let's suppose we have such a bipartite graph. Then first of all, I want to describe what happens at zero vertices. And here's the remark that if you consider zero means circle vertices or white vertices. White vertices of my graph gamma m, it's very easy to see that they're the same things as triples of integers a, b, and c, such that their sum is m minus 1, and they're non-negative. Indeed, so in this situation, you have three white vertices, and so if this is a flex a, b, c, which we think is attached to the vertices, then for example, this one has, you can assign to this 1, 0, 0, and so on. Next, if you talk about the black vertices of this particular graph gamma m, they in one-to-one correspondence with a similar solutions, but of a different, slightly different equation, a plus b plus c equals m minus 2. And indeed, you see that in this case, you have only one solution. This solution is 0, 0, 0, and this is a solution which you assign to this black vertex. I'm talking only about internal vertices. I will never need, so this external vertices, so I will not, oh, I can delete it. So I'm not going to use external vertices now. Okay, so this is the data, the combinatorial data, and now comes the definition of this vector bundle disconnection. So first of all, you put at the white vertices, which are labeled by the three integers a, b, c. You put the following line, it's AA, intersect with b sub b and c sub c, and notice this is a line. And why is this a line? Because you have minus 1 here. So that's why it's a line. And on the other hand, if you have black vertex, then we can make a plane which corresponds to this black vertex. And this is defined by exactly the same formula. A sub a divide intersect b sub b intersect c sub c. And this is a plane. And why is this a plane? Again, because it's a plane because you have 2 here. It's codimension 2. All right. Now, I claim that we have the following diagram. That if you consider any black vertex and consider this vertices around it. So black vertex given by numbers a, b, c, but the numbers assigned to the white vertices are the same, except one of them is bigger by 1. A, b plus 1, c. And then it's very easy to see that you have a triple, that the corresponding lines sitting over this vertices, they all sit inside of this plane PABC. So why this is so? Because you have a plus 1, it sits inside of a sub a. And so this is how this explains how you can get this arrow and so on. All right. So now we have for black vertex, we have this plane and 3 lines sitting in this plane. What we can do, we can make a new line. This will be my black line, again, LABC, and it's defined as just a kernel of the map from these 3 planes. A, B plus 1, C plus L, A, B, C plus 1 to the plane, A, B, C. So that's a line, and you can check that conditions as a flexor generic just gives you that. And so all in all, we got a flat connection. We get a flat connection on a line bundle on the graph gamma m. Where is this flat connection? Well, here, because we have this line L dot sitting here, and then there are these lines L white sitting there. You can introduce the numbers the same way I did before. For example, this is ABC, this is A plus 1 BC, and so on. And so you have lines and arrows, that's a flat connection. Okay, so this is construction one way. Any questions so far? Okay, now let me remind that what I want to do, I want to construct equivalence. So far I start with generic triples and I got flat connection. Now I want to start with flat connection, get generic triple. So let me do it now. So this I can call it reconstruction functor. R. And so what it does, it takes a flat line bundle on the graph gamma m, and it produces out of this generic triple of flex. So how you do this? So let's call this flat line bundle L sitting here. And then what you do, you take direct sum of fibers of this flat line bundle in all black and white vertices. So this is internal black and this is white W. And then the connection by using the parallel transport, you get an operator which acts on the first direct sum to the second one. All we need to do is to take the co-kernel of this operator. And this is our vector space, m-dimensional vector space. So let's look. So if you have, for example, this picture, then we have here 3 white vertices and 1 black vertex. I'm not talking about external ones. And so 3 minus 1, 2, so you get 2-dimensional quotient. But in this 2-dimensional quotient, you immediately see filtration because what you can do, you can filter your map by looking at this picture like that. And then this induces your filtration on your flag. I'm going to do different. Oh. Okay. So look, so if you have such a picture, so now I have, again, you can count that you have exactly 3-dimensional quotient in this case. But then here to do the filtration, you just look at this graph as follows. And then you will see that if you filter your source and target by looking at everything which comes inside of these domains, which are below red, then you will see that this complex has a filtration, and so on the kernel you also have filtration. So this is your flex. Your flex.
May I ask you sort of stupid question, but I should have asked it before. So the fact that you use a skew field and not just an associative ring is that you take quotients, so you want to have free modules. What prevents you? What prevents you from doing the same thing for an arbitrary associative R?
Nothing. So I have this very simple construction of linear algebra. You can do this over every ring, but if I want to formulate a statement, I will be somewhat uncomfortable in general because I would have to put conditions that some expressions in my ring has to be invertible. Since I don't want to keep this this condition with me all the time, I say, okay, let's consider skew field and don't talk about this. But you're absolutely right that this construction is the constructions works over any field or any associative ring.
Mm-hmm.
Just the statements, you need to be a little more careful with the statements. Okay. So okay, so that's it. Theorem is proved because it's easy to see that these constructions, so maybe not that easy, it depends, but these constructions are inverse to each other, and so the theorem is proved. Okay. How about using this? So we can immediately have a generalization. So now let's suppose that you have some surface. Like that. And so the surface has some points on the boundary, some punctures, something like that. So this will be my decorated surface S. And then I wanted to consider some moduli space, let's call it X MS. It's a moduli space of moduli space of local systems of rank M of this R-dimensional vector spaces over R plus invariant flag near each marked point. So it's not the moduli space of local systems, it's a little more because I fix my invariant flags near each of these points, but it's closed. Generically, it's one is finite cover of the other. And then there is the next theorem, which says that this moduli space of stack XMS has a cluster, a non-commutative. I have to explain what this cluster Poisson structure equivariant under the mapping class group, the usual mapping class group, because that's, so to speak, the regular situation. Of S. Now, I need to explain what all this means because what is cluster Poisson structure? It's at this point, it's unclear. And the second statement is the second equivariant. Now, to explain this, what this means, this is done as follows. So we define, we consider some bipartite graphs. They are ribbon because they're embedded on S, which are homotopy equivalent to S. One can call them GLM graphs. I'll tell you what these graphs are in a second. And if you want to know a detailed story about all this, you can look my paper, 1607, 0, 5, 2 to 8 about this kind of graphs. And so here's an example of such graph. So let's take an ideal triangulation of SS. This means that we just subdivide this on the triangles. And then for each of the triangles, we put inside our graph gamma m. And then altogether, we get a certain graph, which I can call gamma m of this triangulation. So for example, if I draw it this way, then you have here black vertices. Actually, okay, so let me draw it real quick. But you can draw exactly the same thing on this triangle. And keep going. So you get some kind of bipartite graph. But you can do more general graphs like that. So the key conditions that when I say it's a GLM graph, there's some condition. The condition is the following. So what is GLM graph on S? So it's a bipartite graph. Let me just say ribbon graph. And then it has the following property. So whenever we have a bipartite graph, there is a notion of zigzag passes. This means that when you travel along this graph, so you turn, okay, let me make it more elaborate, this graph. Oh. So this means that you turn, for example, right at every white vertex and left at every black one. And so the result is a graph like that. So it's actually oriented. And if you do this on this example, actually, I just realized that I'm changing my conventions, who is black and white. So forgive me because I don't want to redraw this picture. But on this case, this bipartite, this graphs will be something like that. And so they'll go like that. And then you can do it in different vertex by different color. Here they will go like that. And so the key point is the following, that whenever you consider your surface and have any puncture on the surface, there will be exactly m of this zigzag passes which circle around this particular point. So every zigzag pass circles around just one marked point, and around, and when it circles around, you have disk here, and there are exactly m of them for each marked point. And whenever you have bipartite graph which has this condition plus epsilon, which I don't want to specify, then this is what I call GLM graph. And then whenever we have such a GLM graph, so there is a theorem that there is canonical birational isomorphism, so that's the main theorem, so to speak, between this Moduli space of stack XMS and the Moduli space of flat line bundles on this graph. This is a GLM graph. And so you have this birational isomorphisms for any GLM graph gamma on S. So this birational isomorphisms, they are analogs of cluster charts. They are non-commutative analogs of the usual. And so if we would be in the situation when this field is commutative, we can just take monodromies of these local systems on this graph and get just the numbers. This would be cluster Poisson coordinates. But in our situation, that's not possible, as I explained before. And so this is the best we can do. And then if you have different graphs, let's say gamma and gamma prime, there is some kind of elementary move, which is called 2x2 move. So it works as follows. So you take a graph which has subgraph of very specific shape, like this. And then you transform to a graph which has a shape of a different kind, like that. And so this is a 2x2 move. The rest is the same. And there is a kind of a basic fact of life, basic fact, that any two GLM graphs on S are related by such moves, by sequence of such moves. So this implies the main thing. This implies that we get equivariant cluster Poisson structure. So the one thing which I did not explain to you, and actually not going to explain in this particular setup, I have to explain what is a birational. So this induced some birational isomorphism between one-dimensional local systems on gamma and one-dimensional local systems on gamma prime. So maybe I skip this, but just saying that this kind of, there's some kind of very simple way how you can correct line bundle here and get a line bundle there, which produce a birational isomorphism, how you can alter line bundle here and get line bundle there. And then you check that there is a pentagon equation for them. And therefore, using these transformations, we get the action of the mapping class group, because whenever you have a surface, and if you consider some element of the mapping class group acting on your graph on the surface, so you get one graph, you get the other graph, so you connect them by the sequence of moves, and you get some explicit coordinate transformation, which relates to moduli spaces of line bundles on those graphs. So these are these non-commutative cluster Poisson transformations. So this tells you what happens with moduli spaces with regular singularities. I probably don't want to go to irregular singularities, but rather than that, I want to explain something which I think is kind of maybe more fun. I want to explain the decorated version.
Sash, did you explain or did you define what is a non-commutative cluster?
I did not tell you, I said, but I can tell you. I wanted to tell you a little later what is a non-commutative cluster A transformations. As usual, with cluster transformations, they come in two versions. And so I decided for this lecture to tell you about non-commutative cluster A transformation and not tell about this one, cluster Poisson. So if you want, I can tell you the cluster Poisson.
No, I mean, you formulated a theorem and promised to explain the words.
Yes, so cluster Poisson transformation by definition in this case is first of all, there are many things to explain. First of all, there is a non-commutative analog of the Poisson structure on those spaces. It's number one. So if you have the space like log 1 gamma on any bipartite graph, then there is a notion of non-commutative Poisson structure. Then when you have two bipartite graphs which are related by this simple transformation, there is some explicit way how you alter a line bundle here. I can tell you how. So if you have parallel transport from here to here, so we want to know how this looks on this different picture where you need to have parallel transport now from here to here. So the question is how, knowing red or left parallel transports, you know the blue or the ones, the right ones. And the answer is that the blue is given as a sum of two things. So you do it. So, okay, so if you consider this transport plus the one which you get going around. So this is by definition the parallel transport which you see here. That's it. So just very simple alteration of the parallel transport, but you get now sum of two parallel transports, and that's where birational nature of these transformations comes. So the sum could be not an isomorphism, and so you have to impose this condition, and that's why it's It's not an isomorphism by birational isomorphism. But other than that, it's just a simple alteration of parallel transport for this 2x2 move. And then anything you can get by composing these transformations is by definition allowed transformation. And then we prove that it preserves the Poisson structure. So that's it. Now, the point is that whenever you have, so in our situation, we have one chart, for example, given by this kind of bipartite graphs related to triangulations. And if you have one triangulation and, for example, do a flip, have another triangulation, then a priori, it's not at all clear how to relate them if M is big enough. For example, if M is any number bigger than 2, a priori, it's not clear that you can relate. You have very different graphs here and here. And then one proves that you can get them as a composition of these 2x2 moves. And therefore, we are done, because what to do with 2x2 move, we know. And it's about M minus 1. It's actually precisely M minus 1 square 2x2 move. So that's it. So that's what the theorem means. Is that okay? Jan.
Well, modulo the definition of the non-commutative Poisson structure, which I still didn't get. I
didn't tell you
understand
the
how,
definition.
yeah, I understand that how you prove that it's without. I mean, the difficult part for me is to understand what this non-commutativity amounts to. What I heard from you in the commutative case, when the Poisson structure is clear. In particular, you have your variety is full of tori, and it's clear why, because it's representations of the fundamental group of the circle, and now how it's kind of upgraded in the non-commutative world, it's a bit, but anyway, it's your talk.
Once again. So we have non-commutative moduli space. Before we had cluster coordinates, which geometrically means we have commutative algebraic tori as open charts sitting inside. Now we don't have this kind of charts, but we have moduli space of one-dimensional local systems on certain kind of graphs. In the commutative situation, they are precisely isomorphic to C star raised to the power given by the number of loops. So that's cluster coordinates, cluster coordinate charts. Okay.
Yes, but and probably you'll get this quasi-determinants just writing explicit.
Yes. But this is in the second version, which I wanted to present you, because in this version, there's simply no coordinates.
Yes. So
you have to make choices to start to talk about coordinates, and you can do this in the decorated version, but here you have to think geometrically about this, just writing this kind of loop passes and linear combination of passes. So that's the cluster coordinates, and you write that in some sense these transformations can be written in coordinates, and then you get this quasi-determinants. That's also part of the business. But also there is a notion of a non-commutative Poisson structure. So it goes as follows: you have a bipartite graph, and then you consider just all loops. Basically thinking, all right, if you give me some kind of graph, how can I make functions on local, if you have a one-dimensional local system on this graph, how can I make functions here? The answer is that you take any loop you like on this graph, and then if you replace R by matrices, by n matrices, then you can talk about monodromy of this n-dimensional vector bundle, take a trace. And so what I'm saying is that, and then you can calculate the Poisson bracket between those traces and ask the question, is it possible to write down the answer in such a way that you are not talking about like entries of these matrices, but talking just with matrices? So the answer is yes, and this device is called non-commutative cluster Poisson structure.
Okay, great. Yeah. This I accept. Okay, good.
Okay, and there is a combinatorial prescription how you do this, so I prefer to skip it. So because I wanted to do something in the decorated situation, which is, as I said, a little, seems to me more kind of fun with formals and so on. So as I said, the main result is non-trivial, I think very much non-trivial, because you have only specific tools, this kind of bipartite graphs and specific transformation of them you can handle. But it turns out the geometry allows you to relate any two of these graphs by the specific moves, and therefore you get equivariant structure. Okay.
Yeah.
All right.
Yes,
Now-
yes. Go ahead.
Huh?
Yes, go ahead. Yeah.
Okay. How much time do I have? I already spoke for 1 hour.
No, go. I mean, you can speak for a minute.
Okay, I'll speak a little more.
Yeah.
So maybe I have like 1 page of my notes. So I wanted to explain the same story in the decorated version. So when I say decorated version, first of all, let's suppose that we're talking about triples of flags, just to give you some idea. So what we do in this case, we say that F is a decorated flag if we are given vectors, let's call them Fi, which lives in every quotient Fi by Fi plus 1, which are non-zero vectors. Then we call this decorated flag. And now I can make decorated analog of theorem A, decorated, which says that generic triples of decorated flags are the same thing as flat line bundles on the graph gamma m trivialized at all zigzag passes. So here it's important to remind you that you're talking about this bipartite graph. I draw this picture again. And so now I can show you once again this this zigzag passes. So here there's one of them like that. And so when I consider my line bundle, it's supposed to be trivialized on these 2 red passes, but it's also supposed to be trivialized on the ones which you see when I go this way. And it's also supposed to be trivialized on the ones which you see if you go that way. So all in all, you have here 6 zigzag passes, and your line bundle with flat connection, which you actually get from the previous step, now comes with extra structure that has trivializations everywhere. And the same in general, so you can do this for graphs which sit on the surface and so on. But the main observation is that when you have an edge of such a graph, there are exactly two zigzags which pass through this edge. So you can go this way, or you can go the other way. But now you have two trivializations here. So you have the red one, let's call this trivialization vector S sub E, and you have the blue one. So this is S prime E. And so now you can just write that one of them, S prime, equals certain number related to the H multiplied by the other. And so these are the cluster coordinates. And so they are assigned to oriented edges, E of your graph gamma. You can do this on any bipartite graph. And they satisfy two kinds of relations. First of all, obviously, if you reverse the orientation, then these numbers are opposite to each other. And secondly, if you have some vertex and you consider the product, so on EM, if you consider the product of these numbers which are assigned to all these edges going in the direction which shows by the cyclic order, you again get one. In fact, if you think more careful about this, you have to understand that we work with so-called twisted local systems. So in fact, the correct sign is -1, but this is something I want to skip, explanation which I want to skip. Okay, so we have now this kind of coordinates. And then the theorem is that, for example, in the situation of local system on the surface, or in the very most general situation of this moduli space of Stokes data, you always have this some kind of bipartite graphs, and you always talk about moduli space of line bounds on those graphs, which are trivialized on the zigzag passes, and so you have these coordinates. But now comes the question, what to do if you have 2x2 move? That's the last thing I wanted to say. Two things I want to say. So if you have this kind of 2x2 move, then you can calculate what happens with your coordinates. So suppose here we had coordinates A1, A2, A3, and A4. And here we have coordinates of this kind. B1, B2, B3, and B4. Then it turns out that B1 can be written as 1 plus big A3 inverse A3, where AI is just the product of all of them starting AI. So for example, A3, I mean, the definition is given here. Then B2 is a similar formula. And plus cyclic shift by 2. So there is a simple explicit formulas, non-commutative formulas, which tells you how you transform coordinates from the edges of the one graph to the edges of the other graph. So that's it. Now you have, after this, you have a definition what is a cluster variety structure. So this means assignments of such non-commutative elements to edges of any graph you have in your story, and then relating any two of them which are related by 2x2 move by this specific transformation. So that's the definition of the A case. And then instead of Poisson structure, there is a non-commutative 2 form. And this is actually surprisingly difficult statement. Everything in this story is simple. This statement, unfortunately, is a difficult fact. Difficult, I mean, there is no simple proof. So you introduce, you work with non-commutative elements A, B of R in any ring, and you introduce this differential form. Now, if you have your graph, you have on edges, let's suppose all vertices are trivalent. You have this number sitting on the vertices, and so you assign to this vertex the 2 form, which is given by A1, A2. This is 2 form. A1, A2 is given by this formula. It's actually cyclically invariant, so you can take A2, S3 or S3, A1, you will get the same result. And then if you have gamma bipartite graph, bipartite ribbon graph, then you can associate to this the form related to this graph, which is sum of omega whites minus sum of the omega blacks. And then the theorem is that this omega gamma is preserved by 2x2 moves, and therefore by any cluster transformations. So the conclusion is that so this implies that on any moduli space of non-commutative decorated Stokes data, I didn't give the definition, but let me just proceed. There exists a canonical 2 form invariant under wild mapping class group. So this is a more kind of explicit version of this kind of Hamiltonian structure of this moduli spaces, because as you have seen, I can write down this form very explicitly. There are coordinates, I can write down this form, and this form is invariant. So it explains the kind of Hamiltonian nature. It's a presymplectic form, so it has a kernel, but it's on the quotient by the zero section, by null section, it induces non-commutative symplectic structure. So maybe that's it for the lecture.
Okay, thank you very much. Very interesting. So questions? So certainly you have not explained all 84 pages of your paper.
No, I explained.
The key, some key point, and
What?
this omega can be also understood in the same way as a Poisson structure, that you consider just matrices, and on the space of R-valued matrices, you have indeed.
You don't have, I introduced it. There is, I mean, like in Poisson case, nobody tells you that such a Poisson structure or such two forms should exist. There's no reason why it should exist.
Yes, but there is this whole the idea of Maxim, you know, that if you want to introduce some structure in non-commutative, for say, you consider just representations, and the structure exists in any representation space.
Yes, but that's exactly what we're just saying. We're saying that if you replace R bar matrices by N matrices, then you get, okay, let me say it again. So in this situation, if you have a graph and you have R ring of matrices, then you consider this n-dimensional connections on this graph. And the statement is that on this complex space of such connections, there is a usual differential two form with logarithmic singularities. And the point is that this two form can be written in such a way that you do not use the internal structure of your matrices, that you write this just using the matrices themselves, their traces, but nothing else.
Also, I mean, since it's already generalization from commutative to non-commutative and something, you didn't speak about the Stokes story, which is huge, but I mean, I heard a couple of talks of Tony Pantev, who did not just stay at the level of usual stacks as you do, but upgraded the story
to
DG stacks. So I'm just curious, what is a non-commutative DG cluster? I mean, cluster transformation.
Here on surfaces, there is no real need to talk about. So Tony probably talked about general notion of DG Poisson structures.
No. He just I heard his talk on Monday of this physics Western hemispheres. No, I can email you his slides. No, he considered just exactly the setup of wild character varieties. It's what was the title of his talk. And it's a running project of him with Stoyan and Dima Arinkin. And they indeed upgraded this Stokes groupoids and whatever probably is in whatever with Bolch, and not only Bolch, but Maxim and myself, it's old story, upgraded to the level of DG stacks, commutative DG stacks. But so I'm just curious, what would be the, I mean, it's not a question to you, but just a question to the outside world, whether there is an upgrade of a cluster, of the notion of a cluster chart, where you replace maybe cluster algebras like naively to their resolutions and so on.
Just, well, this is indeed true, but this, if you want to sit on surfaces, then you need to talk not about just this modular space of Stokes data, but you need to already to talk about some complexes. Then you have a DG version of all that. So you're basically talking about modular space of constructible complexes sitting on this surface with certain properties. And then it certainly should have derived Poisson or symplectic when it's the created structure. And those moduli spaces which appear here, they're just the ones where you don't need derived. So they're just the usual varieties.
Yeah, okay, but I can make kind of another related comment or question, I don't know. It's about this R. You know, this Betty story in the commutative case, irregular, wild, this Betty site can be interpreted in terms of the certain Fukaya category. So that's, I looked kind of briefly before the talk, I looked at your paper with Maxim, and it's related to my own project with Maxim, but basically those discrete data which you mentioned at the beginning, these loops about singularities, they give rise to certain Lagrangian subvarieties, subconic Lagrangian submanifolds, and the cotangent bundles to your surface, just conormal bundles to these loops. And so you can take the Fukaya category of this cotangent bundle and consider a subcategory generated by these conormals and the zero section, which means your Riemann surface, maybe without some small disks. It depends whether you want all the modules or just local systems, as you probably remove some small disks about singularities. All right, so then the Riemann-Hilbert, this Deligne-Malgrange, it can be formulated as an equivalence of the de Rham side, like bundles with meromorphic connections and some prescribed singular behavior at these points, and this Fukaya category, which I just mentioned, the Fukaya category generated by these conormals, and the zero section maybe with some small disks removed. Great, but this is all commutative. Now you have an upgrade to this arbitrary, at least skew field R of the this Betty side as a character variety. I'm just really curious whether I can upgrade the Fukaya category.
No, this is certainly what you said. This is exactly what we do. This is one version that we can consider this in terms of Fukaya category, but we prefer to make emphasis in a different way, because you can talk about this Fukaya category, but we in the paper, the main object in the paper we're talking about is what we call admissible DG sheaves. So if you have any surface and any collection of curves on the surface, so we define some class of complexes of constructible sheaves which are not sheaves, and you can say that their property is that they have microlocal support on those curves.
Yeah, that's exactly.
But. So we define precisely what is the objects we're dealing with. And this actually, first of all, this can hardly be done without DG language. And so and secondly, it's a little strange objects like perverse sheaf, because this is, so what we define is the complexes of sheaves on the complement of the zigzag passes. These zigzag passes are precisely this Lagrangians, the econormal bundle are precisely the Lagrangians you were talking about. So that's why they're so important, this bipartite graph and zigzag passes. But then we define on the surface complexes of constructible sheaves with certain properties. They can be concentrated at most 2 degrees. And so they're not complexes of sheaves, but they can be concentrated in 2 degrees. That's crucial. And their main property is that they're invariant under certain movement of your Legendrian things, this curves which sitting here, but not all. Not all. The key point is that they're not, first of all, we do not assign them to kinds like that, although okay, maybe one could do. But the key point is that when you deform them, you deform them in the class of Legendrian curves, but not all of them. Certain deformations are not allowed, and they will destroy this property.
These are these are Legendrian links, which are intersections of conormals with a contact boundary at infinity.
No, of course. Yeah, I understand, you understand. But the point is not this. The point is that this is some kind of category which is assigned to this kind of curves. You can say this is microlocal sheaves which support on the way, whatever. But the point is that there is a general theorem that if you consider this derived category of constructible sheaves, or you can talk about, anyway, let's do it this way, constructible category of constructible sheaves, then if you have any deformation, Hamiltonian deformation of the singular supports, any, then it provides equivalence of such derived categories.
Yeah,
so all this
theorem of Aniola, or I forgot whoever, but
not
it's been
Aniola, it's Kashivara, Shapira, and sorry. This recording.
They reproved it anyway. It's I understand what.
Maybe we stop recording because I didn't.
No, it's very interesting. Maybe we can stop recording, but I will not see you in the court, so you can say something which is not wrong.
No, I don't remember some spellings or so. I just don't want to say something, but. Anyway, so but this is a key point. There is this remarkable theorem which says that the category of all derived category of all constructible sheaves is invariant under Hamiltonian moves under Hamiltonian under symplectomorphisms. So it moves category supported on one Legendrians to category supported on the image of those Legendrians. So what we do something similar but different, which is not follows from this and different from this, because first of all, we consider not all constructible sheaves, but some subclass of constructible sheaves, and that's very important. Secondly, this subclass of constructible sheaves, it's a DG sheaf, so and it is preserved by some of these transformations, but certainly not by all of them. So if you apply any microlocal transformation, you destroy the property, which means this admissible DG sheaves property will be destroyed. But it's invariant under some of them. And using this, the proof of the main result becomes just one line, because what we do, we say that if you have the surface and you have the zigzags, I was talking about zigzags, but that's of course secretly this Legendrians we are talking about here. And the key property of this zigzags, which lives on bipartite graphs, they look very complicated, that they can be isotope to this collection of concentric circles around the punctures. Then if you look on the definition of this admissible DG sheaves in this case, so this admissible DG sheaves give precisely this moduli space XMS as a stack. Precisely, not more, not less.
Do you understand correctly that in the commutative case, your cluster tori would be just C-star local systems on the unions of this? So you have Lagrangians, yeah?
No.
Typical.
Jan, not correct. No.
Why?
I mean, correct and not correct. So, so this is right, but we are talking about bipartite graph. Okay.
Yeah.
So we consider local systems on bipartite graph. So if you just draw a picture, okay, let's suppose this is a part of the bipartite graph. Then, actually, I have to explain more geometry to be able to talk about this. So we produce, the story goes as follows. If we consider situation when these Legendrian curves are very simple, so this is what I called ideal or GLM webs. This is GLM webs where the zigzag passes goes concentrically, can be isotope to concentric around each mark point. Then from the definition, it follows that our DG shifts, if they also vanish near each mark point, additional condition, then this is just by definition, they deliver modular space of local system with filtrations. Okay? If they don't deliver, for example, complexes of local systems, or anything like that, they deliver plain local systems with filtrations. And for example, filtrations come from these concentric circles. Not more, not less, it's precisely that. On the other hand, if you start to deform them and you deform them to zigzags of certain bipartite graphs, then you see a different picture. Then it's not that when you deform them, that somehow you get really constructible sheaves which live on the whole surface, and their support is very, I mean, those also live on the whole surface, but the guys which live here, they live on the whole surface, but because of the conditional admissibility, they can be expressed as a local systems on this graph. Okay, it's a statement that the definition of admissibility is such that in the case of bipartite graph, and only in this case, you can express an open part of this category admissible DG shifts as local systems on this graph. And it's not quite.
So when you say this graph is what?
We have we start with a bipartite graph.
Yeah.
It's important that bipartite graph, not any graph. So it has black and white vertices. Okay. So then there is a notion, then this, as any bipartite graph, it has its zigzag passes. They go left and right, okay?
Mm-hmm.
And we consider DG shifts which live everywhere, like here, here, but they have property, they have certain property, which in particular means that the singular support lives only on the zigzag passes. They live on the whole surface, okay? Then we consider, so if you look, I draw the zigzag passes this way, just to be concrete, and this gives me co-orientation because they oriented zigzag passes. So if I consider modular space of this admissible DG shifts, which are postulated to be 0 here and 0 here, then it will look like this. This will be in degree -1, and this will be in degree 1, and there will be canonical arrow here.
Oh, so yeah. And now I understand what you mean. Yeah. Okay.
So this is consequence of the definition of admissible shifts, but it's not consequence of any general machine, so to speak. So when you can say that we consider some subcategory of Foucault category, but again, this definition is you cannot make it short. I mean, you cannot make it simpler. That's what I'm saying. So what I'm saying is that you can talk about derived category of constructible sheaves, or you can talk about Foucault category. So as we know, Foucault category.
I can recover the abelian category from that as well. But
this is not the abelian category of constructible sheaves. It's a different category. That's the point. This is something strange which we didn't see before. So there's so you have all constructible sheaves, and then there is derived category of constructible sheaves, and then there is something else.
Hold on. So let me just make it clear. So if you have a regular connection, so you have this your what you call discrete invariant, this Stokes curves about singularities. You can consider them up to isotopy, everything up to isotopy. Great. Yeah. Now you can consider constructible sheaves with a microlocal support, which belongs to the conormals to these curves, and maybe to the zero section minus the singularities.
Yes, you can do this.
All right. Now, this is okay. The category which you are talking about, how it is related to the category which I just described.
This is this category exactly. Precisely this category. But this is all good only because this is such a simple situation when all these curves are near the points. If I wanted to define cluster structure on this modular space, I cannot get away with what you're saying. That's the point.
I see. Okay, so you did not object the category which
I do not object the category. I object the way how you
cluster.
reinterpret
I
this.
see.
So, for example, so we talk about this admissible DG sheaves. So the first point is that they're not sheaves or complexes of sheaves. They're DG sheaves. This means that they have data. They have non-trivial data of homotopies. Homotopy is a part of the structure. And so, for example, in this case, when I was saying that you get this arrow is a homotopy.
Yes, I understand. Yeah.
So if you don't talk about homotopies and don't talk about DG sheaves, you don't have this arrow.
And you say that the cluster structure.
Cluster structure is this arrow.
It depends. Okay. I haven't thought about cluster structure indeed. I thought about Riemann-Hilbert, and for that I need just a category. And
For Riemann-Hilbert, it's a well-known fact. I mean, to classics that this category of this beta data or whatever. So this is just vector bundles on this with filtrations. As for example, the Lagrange the way they do it, or any other way. Just data of some vector bundles with some filtrations with jump. All right. So you can express this notion as the category of this admissible DG sheaves in some simple, I would say, trivial situation for those curves sitting around these points. And that's a trivial reformulation. So nothing happens, you don't see any homotopies, nothing. But then when you start to deform this, so we use the fact that you can deform and that, for example, when you go like this, you can go like that and so on. That if you go like this, you can change it and go and, make it disjoint. So when you make this kind of transformations, they act, of course, on all derived category of constructible sheaves, or no questions. But they also act on this DG category, preserving this admissible DG sheaves, which is a certain fact. And we use this fact. So, for example, when we do these moves, we keep track of those homotopies. So on original station here, there was no here. We didn't talk about those homotopies because all of them were trivial. But when we start move, we pick those homotopies. And in the end of the day, when we transform them to the bipartite graphs, actually our data becomes very, very simple. So many of these stocks on many domains will be just zero, and the other will be one-dimensional, but there will be this additional data which corresponds to those homotopies. And those homotopies are the local systems.
And you need to deform because you want this mapping group wild invariance.
No, not only for this. So if I want to talk about the cluster structure, it's not wild also, but if I want to talk about cluster structure, if I keep talking about these curves which are sitting around these special points, I don't see anything interesting. Okay, they can go like that. But all you see, you can express in the standard language of vector bundles with filtrations. You don't need any new machinery to talk about this. Just plain vector bundles with filtrations with jump. Okay. Or you can just say this is a collection of this both Samuelson varieties or cluster varieties relate to elements of the braid group, as we defined this with Volodya-Fock long ago. This is known objects. But when you, if you want to get cluster structure on those objects, you have to deform them. So what we do, we find in this big Moduli space, we find some open subspace, explicitly given open subspace, this torus, so to speak. And in order to find this torus, you have to introduce some additional data. So you have to introduce this bipartite graph because they correspond to bipartite graphs. If you don't have bipartite graphs, you have nothing. If you do have bipartite graph, then what we say is that if you look at the description of this admissible DG sheaves in the context of bipartite graphs, then again, by their definition, you see that they're just flat connections on those bipartite graphs. It's some observation. And those flat connections, they are key ingredient of those homotopies. But then, since you can deform one collection of curves to the other, and since we can keep track of those DG sheaves, keeping track of those homotopies and so on and so far, if you put this together, you see that this open torus sits inside of the big Moduli space. This is a cluster structure.
I understand. It's certainly it's more complicated. Indeed, you cannot get cluster structure for free.
Yeah, you cannot get it for free. You can talk about this. Once again, this is a classical thing. You can talk about this curves and local system of this curves, which has filtrations and they jump and so on and so forth. This is a way to talk about Stokes data, but you don't see cluster structure this way.
Yeah. Deligny-Malgrange didn't have clusters.
No. It's a to see. I'm just repeat again this point. To see cluster structure, you have to introduce more general notion of this admissible DG sheaves, which again in this example it's so trivial that you don't need to talk about them. This admissible DG sheaves in the case when we talk about this curves near marked points. First of all, they're not DG sheaves; they're just sheaves. They're just constructible sheaves. That's all. But and you don't see cluster structure. But when you talk about DG sheaves related to curves which already start to intersect, so what you're doing, you move this zigzag passes in such a way that they start to intersect in a very dramatic way. For example, remember the picture. The simplest possible picture is this. So you have this bipartite graph. So if you draw the zigzag passes, then there are, as I just was explaining, they go like that, or they go like that, or they can go like that, or they can go like that, but they intersect. That's what I'm saying.
Mm-hmm.
I just want to draw this again so you see what I'm talking about. They intersect. And they intersect, and it's very different from the picture which you draw if you move all them to the vertices. Then you see picture like that. Okay, and so the claim is that they're isotopic. This is easy, of course, but here you see this three flags by definition, because this admissible DG sheaves, whatever. In this case, this is just a vector space with three filtrations by definition of how we define this things, and there is nothing new here. But when you talk about this DG sheaves here this is something new, because you have to, here there is no homotopy, no this kind of DG structure, a non-trivial one. Here there is one, and it gives you precisely the connection on a different object, not on this passes, but you have now connection, because the connection lives on this graph. And this connection is actually, it's all built from homotopies. Okay?
Mm-hmm. Mm-hmm.
And so when you deform one to the other, if you just trace the equivalence of categories on the level of derived category of constructible sheaves or Fukaya categories, which in this case is the same, you lost information. So you lost this flatline bundles are completely lost, because they're described in terms which are not in your language on Fukaya category or constructible sheaves. They are not there.
Maybe. I mean, the way you explain it, yeah, it looks like some structure is missing, but I'm not 100%. I can, yeah, this notion of zigzag path, it's somehow, yeah, it's not incorporated in the Fukaya. Okay, let me think about that.
Yes, the crucial thing about the zigzag passes, so they're curves, but then there is a condition when the other curves intersect them, they go like that. And this is used crucially, absolutely crucial, in order to get this line bundles and so on and so forth. So yeah. It's if I just draw you some collection of oriented lines, I'll get nowhere.
Yeah, it's kind of, it was simply kind of the idea to get tori for free, or almost for free, just to look for C-star like objects of the Fukaya category.
Exactly. But this is, you have to be very careful. So when you start talking about Fukaya category or constructible sheaves, you have to be very careful what you're talking about.
Yes, so it's,
so if you don't say that you consider DG objects, then it doesn't work.
Yeah, okay. Yeah, I understand your point. Now, are there any other questions?
After this little short question from one of the organizers.
Yeah, but it was very interesting. All right.
I have to ask a question. So
yeah. Okay, good. if
So
you
you use the generic triples.
Sorry, what?
What happens if you have a generic quadruples or higher? Because this
Oh, same
is,
thing. So that's a good question. So if you have quadruples of flags, you just draw a rectangle and you put your flags here, A, B, C, D. Then you do triangulation, insert here your bipartite graphs the way I just did, here and there. And then you consider local systems on this particular bipartite graph. And you clearly see that you have exactly one non-trivial loop here. So this is this loop. Oh. And so that's the cluster, the usual cluster coordinate in this case, we call it like X, which corresponds precisely to this diagonal. And so in this case, we got it from the geometry of the bipartite graph, just this way. And again, this is not new. If you take, for example, my paper on this ideal webs, that's exactly what this paper says, how you proceed with this. But what is new in this situation, not only that you can do this non-commutatively, but basically one of the main points is what we discussed with Jan, that you can explain why these coordinates without doing any computations whatsoever. So you can just deform those curves and prove lemma that under deformation, this admissibility holds. This immediately implies a statement because those zigzags in this case, they are equivalent to this collection of zigzags. And this by definition is, if you look at the definition, this provides you 4 flags in the space. And this provides you cluster coordinate.
I see.
Okay.
So the reason of the bipartite graph is always is regular over valence 3.
No, it's valence 3 doesn't play any role. It's not important. It just have, actually even here it's not a valence 3 if I draw all vertices. That's not important at all. What is important is that the collection of its zigzag passes has certain property. I was trying to explain it here. And so you can, talking about bipartite graphs is the same thing as about talking about its zigzag passes. But I insist that these zigzag passes come with certain property, which is key in order to get a cluster chart. Without it, you don't get it.
Okay, I do have a second question. Probably you didn't whether I don't know if you consider. So the generic triples or generic quadruples, this form a closed subvariety into the product of the flag varieties. And so does this have some kind of description in terms of group elements?
I guess you're referring to the following phenomena that you have this Briard decomposition. So you have a pairs of flags, right? Then Yale group comes as a thing which parameterize these orbits which are not generic. Similar things happens here, yes.
Okay. I see.
But I'm talking about generic, but I can talk. Basically, talking about the Stokes data is just incorporating arbitrary flags, not generic ones. It's in a certain sense. So
I see. So that's the word where the generic comes from the intersection.
What I said is not 100%. I mean, I have to elaborate on this, but basically, yes, one can allow arbitrary configurations of flags. Yes.
Okay. Okay. Well, thank you very much.
What is very nice for me and very surprising for me that this bipartite graphs is enough. So it may happen that in order to describe this cluster structure, even the commutative ones, you need something, you need some other devices. For example, if you're working with a group G, which is different from GLN, then these bipartite graphs, they are not helping at all. You need very different methods. And so any group different than GLN is a very, very, very different story and much more complicated story. But here, this bipartite graphs is enough for all Stokes data, number one. And secondly, they're so much enough that even non-commutative case can be done. So that's very nice feature. And which
at the beginning, I was wondering for the generic pairs whether they are somehow just motivated from the double group cells, or do they have anything to do with the double group cells? for the generic curves.
So once again, you can describe arbitrary case. Yeah. Just need to draw more pictures, so to speak, but it's not dramatically different.
Okay, well, thank you. Thank you, Sasha.
Okay, so I think since it's not just one, it's almost 2 hours. So Sasha, thank you very much for your talk. Very interesting. And I recall you that I asked you to send the notes.
Oh yeah, but not. I mean, in a couple of days, okay?
Yeah, okay, but please don't forget it. Okay, thank you.